Welcome to this scientific lecture on how artificial intelligence is being used to replace traditional professors and teach an entire semester-long course in microfluidics. This is a cutting-edge development in education technology that has profound implications for the future of higher education. Microfluidics is an incredibly complex field that requires deep understanding of fluid mechanics, chemistry, biology, and engineering principles. Traditionally, this requires a highly trained professor with decades of experience. A traditional professor brings years of education, a doctorate degree, research experience, and teaching expertise. They understand not just the material, but how to communicate complex ideas to students with varying backgrounds. The artificial intelligence system designed to replace this professor uses a sophisticated multi-layer architecture. Let me show you how this system is structured. The system consists of 4 primary layers that work together. The knowledge base contains all the microfluidics content. The pedagogical engine determines how to present this information. The adaptive learning layer adjusts to each student's pace. And the assessment module continuously evaluates understanding. Let me explain the knowledge base in more detail. This is where all the course content lives, structured in a way that an AI can access and manipulate. The knowledge base is organized into interconnected modules. Each module contains detailed information on specific topics like fluid dynamics equations, laboratory techniques, fabrication methods, real-world applications, the necessary mathematics, and case studies from research papers. Let me give you a concrete example of how the AI teaches a fundamental concept, the Reynolds number. This is a dimensionless quantity that predicts flow patterns in microfluidic devices. The Reynolds number equals density times velocity times characteristic length, all divided by dynamic viscosity. The AI doesn't just present the equation, it breaks down each component and explains the physical meaning. For low Reynolds numbers, below 2300, we get laminar flow. The AI shows animated diagrams where fluid particles move in parallel layers, with no mixing between layers. This is typical in microfluidic channels. For high Reynolds numbers above 4000, we get turbulent flow. The AI shows chaotic, swirling motion with eddies and vortices. This is rare in microfluidics, but important to understand for scaling considerations. Now let's do a back-of-the-envelope calculation to show why microfluidics is almost always laminar. The AI guides students through this reasoning process. Consider a typical microfluidic channel with width 100 micrometers, which is 10 to the negative 4 meters. Typical flow velocity is 1 millimeter per second, which is 10 to the negative 3 meters per second. For water, density is 1,000 kilograms per cubic meter. Water's dynamic viscosity is about 10 to the negative 3 Pascal seconds. Plugging these values in, 1,000 times 10 to the negative 3 times 10 to the negative 4 divided by 10 to the negative 3 gives us Reynolds number of 0.1. A Reynolds number of 0.1 is extremely laminar. This means microfluidic systems have very predictable, controllable flow patterns. The AI uses this calculation to build intuition. Now let's examine the pedagogical engine. This is the component that decides how to sequence information and adapt explanations based on student performance. The pedagogical engine takes student input, processes it through machine learning algorithms, and produces customized educational content. It's continuously learning from thousands of student interactions. Here's a concrete example. Suppose a student is struggling with the mathematical prerequisites for understanding the Navier-Stokes equations. The Navier-Stokes equation, density times the quantity partial derivative of velocity with respect to time plus velocity dot gradient of velocity, equals negative gradient of pressure plus viscosity times the Laplacian of velocity. The AI detects through quiz responses and problem-solving attempts that the student doesn't fully understand the del operator and the Laplacian. The AI automatically inserts a mini-lesson on vector calculus. It shows visual representations of gradient fields, explaining how the del operator creates a vector that points in the direction of steepest ascent. The gradient operator del equals the vector of partial derivatives. Partial with respect to x, partial with respect to y, partial with respect to z. Once the AI confirms understanding through targeted exercises, it returns to the microfluidics content. The student now has the mathematical foundation to properly understand the Navier-Stokes equations in the context of microchannels. The third layer is adaptive learning, which personalizes the pace and depth of instruction for each student. This is something a traditional professor cannot do for a class of 50 students. Student A might race through basic concepts and dive into advanced topics like droplet microfluidics and organ-on-a-chip applications. Student B progresses at a standard pace. Student C receives additional support and more examples for each concept. Critically, all three students complete the same learning objectives and demonstrate mastery of the same core competencies, but they get there via different paths optimized for their individual learning styles and background knowledge. The AI provides real-time feedback during problem solving, something that's impossible for a professor grading assignments days later. When a student designs a serpentine mixer, the AI immediately analyzes the geometry and provides feedback. It might say, "Good serpentine design. This will enhance mixing through chaotic advection. Your channel width-to-height ratio will produce the desired Reynolds number." The fourth layer is continuous assessment. Unlike traditional courses with 3 exams, the AI evaluates understanding constantly through hundreds of micro-assessments. Each green square represents a concept mastered. A red square triggers immediate remediation. The AI builds a detailed map of each student's knowledge state across hundreds of microfluidic concepts. Now let's look at quantitative data on effectiveness. How does the AI compare to traditional instruction? In controlled studies, students taught by the AI system scored an average of 84% on standardized microfluidics assessments compared to 72% for traditionally taught students. That's a 12 percentage point improvement. This difference is statistically significant, with p less than 0.001, meaning it's highly unlikely to be due to chance. Course completion rates increased from 68% to 91%. The AI's adaptive pacing and immediate feedback reduce student dropout significantly. Let me give you an analogy to understand how the AI teaching system works. Think of it like a master chess coach that has played millions of games. Just as the chess AI has analyzed millions of positions and knows the optimal move in any situation, the teaching AI has analyzed thousands of student learning trajectories and knows the optimal instructional strategy for any knowledge state. The AI recognizes patterns. When it sees a student struggling with a specific concept, it matches that pattern to thousands of similar cases and applies the intervention that was most successful historically. However, there's a critical limitation. The AI cannot teach hands-on laboratory skills. You cannot learn pipetting technique or cleanroom procedures from a computer screen. Microfluidics requires extensive hands-on training. Using a micropipette, operating a syringe pump, aligning microchannels under a microscope. These are physical skills that require practice with real equipment. The most effective implementation uses a hybrid approach. The AI handles all theoretical instruction, problem sets, and conceptual understanding. A laboratory instructor provides hands-on training in practical techniques. This hybrid model reduces required teaching staff by approximately 70%. Instead of 3 professors and 4 teaching assistants, you need 1 lab supervisor and the AI system. Let's examine the economics. What does it cost to develop and deploy an AI teaching system versus traditional instruction? Initial development cost for the AI system, approximately $2 million. This includes software development, content creation, knowledge base engineering, and testing. Annual operating cost, about $50,000 for cloud computing, system maintenance, and content updates. If the system serves 500 students per year, that's $100 per student annually. Compare this to traditional instruction. A professor's salary plus benefits averages $150,000. For a class of 50 students, that's $3,000 per student. The AI system provides a 30-fold cost reduction per student. The initial investment is high, but it scales extremely well. Now we must address the ethical considerations. Replacing professors with AI raises important questions about the future of education and employment. First concern: students lose the human mentorship and relationship with the professor. This is particularly important for graduate students who need career guidance and research direction. Second concern: This technology could eliminate thousands of academic positions. If one AI system can teach 500 students, many lecturer positions become obsolete. Third concern. AI-optimized learning might prioritize measurable outcomes over deeper critical thinking. Students might learn to pass assessments without developing true scientific intuition. However, proponents argue this technology democratizes access to world-class education. A student in a developing country can receive the same quality instruction as one at a top university. The same high-quality AI teaching system can simultaneously serve students at MIT, in rural India, in Africa, and in online programs. Geographic and economic barriers to education are reduced. Let me briefly explain the neural network architecture that powers the pedagogical engine. This is cutting-edge deep learning technology. The system uses a deep neural network with multiple hidden layers. The input layer receives student performance data, demographic information, and learning history. Hidden layers process this information through hundreds of thousands of weighted connections. The output layer produces the next instructional step. Each neuron performs a weighted sum. Y equals the sigmoid function of the sum of weights times inputs, plus a bias term. This network was trained on data from over 50,000 students taking microfluidics courses worldwide. It learned which teaching strategies work best for different student profiles. The system also uses advanced natural language processing to generate explanations in natural, conversational language, similar to how a human professor would explain concepts. When a student asks a question in their own words, a large language model similar to GPT-4 parses the question, retrieves relevant information from the knowledge base, and generates a natural language explanation tailored to the student's level. For example, a student might ask, "Why does my microfluidic channel keep getting clogged?" The AI considers multiple possible causes: particle size relative to channel dimensions, surface chemistry and protein absorption, air bubble formation, inadequate filtering of samples, or fabrication defects. It then asks targeted diagnostic questions to narrow down the actual cause. What's your channel width? What's the particle size distribution of your sample? Are you using filtered solutions? This mimics how an experienced professor would troubleshoot. Looking to the future, next-generation systems will incorporate multimodal learning, combining text, video, virtual reality, and even haptic feedback. Students could practice micropipetting in virtual reality before touching real equipment. The VR system provides force feedback, so you feel the resistance when drawing up liquid. Augmented reality overlays during physical lab work could provide real-time guidance. The system might highlight which valve to turn or display the correct flow rate settings overlaid on your actual equipment. Some researchers are even exploring brain-computer interfaces to optimize learning. This is highly speculative, but scientifically fascinating. EEG sensors measure brain activity in real time. When the system detects confusion through specific neural signatures, it automatically provides additional explanation or a different approach. The system could measure cognitive load and attention. If it detects that the student is mentally overloaded with too much information at once, it slows down the pace. Despite all these capabilities, there are aspects of professorship that I fundamentally cannot replace. Let's be honest about the limitations. Original research creativity. A human professor might notice an unexpected result in the lab and pivot to explore a completely new direction. AI follows patterns but doesn't have genuine scientific curiosity. Serendipitous insights during office hours. Sometimes the most valuable learning happens in unplanned conversations where a professor shares hard-won wisdom about research careers, scientific ethics, or life as a scientist. Deep mentoring and career guidance. And I cannot write a truly personal letter of recommendation based on years of knowing a student. It cannot provide the nuanced advice about which postdoc position to accept. So what's the verdict? The most likely future is not pure AI teaching or pure traditional teaching, but a sophisticated hybrid. AI handles the scalable parts: content delivery, practice problems, assessment, and adaptive pacing. Humans handle the parts requiring genuine relationship, creativity, and wisdom. Together, they provide better education than either could alone. This isn't science fiction. It's already happening. Let me give you specific examples of deployed systems. Georgia Tech's online master's program uses AI teaching assistants to handle tens of thousands of student questions. Students often can't tell they're talking to an AI. Carnegie Learning's AI-driven math curriculum is used by over 600,000 students in the United States. It adapts in real time to student performance. The specific microfluidics system I've described is currently being piloted at 3 universities with a total of 230 students. Early results are extremely promising. Let me show you more detailed performance data from the pilot program. The data is compelling. Higher exam scores, dramatically better completion rates, reduced study time required, and higher student satisfaction. The efficiency gains are real. However, there's an important challenge: maintaining academic rigor. There's a risk that AI systems optimize for student satisfaction at the expense of difficulty. And AI optimizing for completion rates might unconsciously make content easier than it should be. This is a serious concern that requires careful monitoring. The solution is external, standardized assessments. Students must pass third-party exams that are not created by the AI system. This ensures rigor is maintained. Let me conclude by placing this in the broader context of STEM education's future. AI will augment, not replace, human professors. The most effective model combines AI's scalability and adaptability with human creativity and mentorship. It democratizes access to high-quality education. A student anywhere in the world can learn microfluidics from a system trained on the best teaching methods. But it requires careful ethical oversight. We must protect academic jobs, maintain rigor, preserve human relationships, and ensure AI doesn't exacerbate educational inequalities. The technology exists today. This isn't futuristic speculation. The systems I've described are operational. The question is not whether AI will transform education, but how we guide that transformation. My final thought: as we adopt these powerful technologies, we must intentionally preserve the human elements that make education meaningful. Education is not just information transfer, it's inspiration, mentorship, intellectual community, and personal growth. I can deliver content brilliantly, but we must preserve the human relationships that make learning transformative. Thank you for attending this scientific lecture on AI in education. The future is being built right now, and understanding these systems is crucial for anyone in academia or educational technology. The revolution in how we teach complex subjects like microfluidics is already underway.